The F-14 Tomcat entered service with a singular mission: intercept and destroy Soviet bombers before they could threaten US carriers. At the Cold War's peak, these high-speed missile-armed bombers posed a deadly risk from hundreds of miles away. The Tomcat, capable of exceeding Mach 2, dogfighting escorts, enduring carrier landings, and wielding cutting-edge weapons and sensors, met that challenge. Its signature swing wing design made it a true aerial shapeshifter. Variable sweep wings. When Grumman's engineers proposed the Tomcat's variable geometry wings, the concept wasn't exactly new. The idea dates back to World War II, when German designers theorized that altering wing sweep in flight could give aircraft the best of both worlds: excellent lift at low speeds and low drag at high speeds. Germany's Messerschmitt P.1101 was the first prototype to feature such wings, but it never flew before the war ended. The US recovered the incomplete airframe, shipped it to Bell Aircraft in Buffalo, and used it to inspire the Bell X-5 in the early 1950s. The X-5 proved the idea could work, but also revealed major engineering headaches that would take decades of advances in materials and aerodynamics to overcome. By the early 1970s, those advances had arrived. The F-14's swing wings allowed it to spread wide for maximum lift during takeoff, carrier landings, and slow-speed patrols, then sweep back tightly for blistering supersonic runs up to Mach 2.3. The titanium backbone. At the heart of the Tomcat's shape-shifting wings sat its most critical structural element, the wing box. This central beam connects the two wings, absorbs the massive bending forces they generate, and ties them into the fuselage. For a heavy, carrier-capable fighter loaded with huge engines, a massive radar, and multiple long-range missiles, the wing box needed to be both extremely strong and as light as possible. Grumman turned to an exotic choice: titanium. Stronger than aluminum, but much lighter than steel, titanium offered the perfect strength-to-weight ratio. The catch? It's notoriously difficult to work with, especially when welding. Titanium reacts aggressively with oxygen when hot, creating brittle oxides that weaken joints. To solve this, Grumman built a specialized facility to perform electron beam welding inside a vacuum. By firing a concentrated beam of electrons, the metal could be heated and fused without combustion, and without oxygen contamination. This process shaved roughly 15% off the weight compared to an aluminum wing box, and up to 50% compared to a bolted titanium design. Breathing at Mach 2. Pushing a large fighter to more than twice the speed of sound requires massive engines, and a clever way to feed them air. Jet engines need subsonic airflow entering their compressors. At supersonic speeds, the inlet must slow the incoming air by carefully shaping and positioning shockwaves. Grumman designed simple box-shaped intakes with 3 computer-controlled ramps that adjusted 40 times per second, optimizing airflow from takeoff to Mach 2+. Bleed air ducts removed slow-moving boundary air from the ramps, venting it over the wings. The designers also oversized the intakes by 10%, anticipating future engine upgrades. Initially, a bleed door dumped the extra airflow, but years later, when more powerful engines arrived, the intakes were ready without redesign. A rocky start with engines. The F-14 entered service with Pratt & Whitney TF-30 engines, a hand-me-down design from the F-111 bomber. While adequate for a heavy strike aircraft, these early turbofans were unforgiving in a nimble fighter. They were prone to compressor stalls during aggressive maneuvers, sometimes leading to catastrophic flat spins. Tragically, this flaw contributed to the 1994 death of Lieutenant 𝐃𝐨𝐧'𝐭, the Navy's first female carrier fighter pilot. Engine position compounded the danger, with the Tomcat's widely spaced nacelles. Losing one engine produced massive asymmetric thrust, yawing the aircraft violently. In 1984, the Navy began upgrading F-14s with General Electric F-110 engines. These power plants delivered 32% more thrust, allowed carrier launches without afterburner, extended endurance by over a third, and were smaller and lighter than the TF-30s. The Tomcat was finally getting the muscle it deserved. The Phoenix and its all-seeing eye. The Tomcat Stinger was the AIM-54 Phoenix missile, a 1,000-pound Mach 5 interceptor designed to swat down bombers before they could fire. No other fighter could carry it, and no other fighter had the radar to make it work. The F-14's AWG-9 radar was a monster for its day. 10.2 kilowatts of output power, tracking targets up to 200 miles away. It could follow 24 aircraft at once and guide 6 Phoenixes simultaneously. In tests, the missile could pull 17 G turns, nearly double double what even the most agile fighters could survive. Despite its capabilities, the Phoenix saw little combat use. The Cold War scenario it was built for, mass bomber raids against the fleet, never materialized, and the $1.3 million price tag meant Tomcats rarely flew with a full 6-missile load in peacetime. The Carrier Dance. Operating from carriers pushed the Tomcat's engineering to the edge. For recovery, its tailhook had to catch arrestor cables at over 120 knots, stopping the jet in just a few hundred feet. In one 2002 mishap, a hook weakened by hydrogen embrittlement snapped off, forcing the crew to eject as the jet fell off the deck's edge. Launches were equally intense. The nose strut could kneel by 14 inches, storing spring energy. When released from the catapult shuttle, usually steam-driven, though today's carriers use electromagnetic systems, the nose popped up automatically, helping the jet clear the deck. From 0 to 180 miles per hour in 2 seconds, the Tomcat's acceleration off the bow beat even the fastest supercars. Wing sweep and aerodynamic magic. The Tomcat's wing sweep could range from 20 degrees for low-speed lift to 68 degrees for high-speed dash. A special 78-degree oversweep tucked the wings neatly for carrier storage. The flight computer automatically adjusted sweep in real time, letting pilots focus on the fight. At low sweep angles, airflow is mostly chord-wise, over the wing's lifting surface. At higher speeds, increasing sweep introduces more span-wise flow, which delays the onset of shock waves and reduces drag. At supersonic speeds, swept wings also help keep the shock cone from the nose from hitting the wing roots. To counter the rearward shift in lift at high speed, the F-14 featured retractable glove vanes ahead of the wings, adding lift near the nose. While effective, they were often removed in later service to save weight and maintenance time. Control without ailerons. The Tomcat skipped traditional ailerons, instead using wing-top spoilers for roll control at low sweep and full-flying horizontal tails, tailerons, at higher speeds. These tailerons used boron fiber composites, a cutting-edge material at the time, combining tungsten wire cores with boron coatings for exceptional strength. Other quirky solutions included inflatable bags that filled the gap between retracted wings and fuselage, smoothing airflow, and a fuselage lifting body design that provided extra lift and reduced stress on the wing pivots. An aircraft of its era. In service, the F-14 proved both beloved and expensive. Its complexity meant it needed 30 to 60 hours of maintenance per flight hour. With the end of the Cold War, its specialized long-range interception role became harder to justify, especially as stealth, multi-role fighters like the F-35 promised more flexibility for less logistical strain. After 32 years, the Tomcat retired in 2006, but its legend endures. It was an apex predator for a threat that never quite came, a technological showcase of material science, aerodynamics, and Cold War urgency. Why the Tomcat still captivates. The F-14 Tomcat remains one of the most recognized fighter aircraft ever built, thanks not only to its combat capabilities, but also its starring role in popular culture. From its sweeping wings to the thundering roar of afterburners at launch, it embodied the raw, high-stakes glamour of carrier aviation. It was also a jet full of foresight, and from intakes designed for future engines to a radar decades ahead of its peers. It showcased daring engineering choices, titanium backbones welded in vacuums, flight computers adjusting shockwave taming ramps 40 times a second, and weapons that could reach across entire states. The Tomcat's story is a reminder that aircraft aren't just machines. They're products of the geopolitical fears, technological dreams, and daring bets of their time. And in the case of the F-14, those bets produced one of the most awe-inspiring fighters to ever touch a carrier deck. And that's the story of the legendary F-14 Tomcat, a Cold War icon and an engineering masterpiece. If you enjoyed diving into the tech, history, and drama behind this jet, smash that like button to let us know. Got your own favorite Tomcat fact? Drop it in the comments below. We love reading them. Don't forget to subscribe. Thanks for watching, and we'll see you in the next flight.